Welcome students. Today we are starting our journey in understanding basic structural analysis in our subject Structural Analysis 1. Now my friends, before we enter into various methods of structural analysis, we must learn what we mean by determinate structures and what do you mean by indeterminate structures. Let's get these concepts very clear. Determinate structures and what do you mean by indeterminate structures. If our concepts regarding determinate and indeterminate structures are crystal clear, we will understand structural analysis in a better fashion. So, up till now, we have dealt with all the determinate structures. You have seen in your strength of material subject and also in engineering mechanics. What is determinate structure? A determinate structure is a structure where you can determine the structural response of a structure using equations of equilibrium alone. Let us say this is the cantilever beam and this is the load of 10 kilonewton which is acting at the free end of this cantilever beam for 2 meter. If you are asked to plot the shear force diagram and bending moment diagram for this cantilever beam, you are in your capacity, you can plot the shear force diagram and bending moment diagram for this. The shear force diagram will be something like this. Okay, 10 kilonewtons. This is shear force diagram, and then bending moment diagram will be 0 at the free end and 10 into 2, 20 at the fixed end. So this is the bending moment diagram, 20 kilonewton meter bending moment diagram, negative. Of course, we will discuss these things in details. You have seen this in your SOM. That is not our point of discussion, that how to draw the shear force diagram and how to draw the bending moment diagram. Our point of discussion is this structure, we can analyze the response of the structure. What do you mean by response of a structure? The effect of the structure, effect of the loads on the structure in the form of shear force diagrams and bending moment diagram. This is my shear force diagram and this is my bending moment diagram. So the effect of these loads in form of shear force diagram and bending moment diagram given is known as response of the structure. If you can analyze the responses of the structure using equations of equilibrium alone. What are the equations of equilibrium? In our first year mechanics, we have seen summation of forces in x direction is equal to 0, summation of forces in y direction is equal to 0, and summation of moments acting in the plane is equal to 0. These three are the equations of equilibrium in plane analysis. When we analyze it in 2 dimensions, when we analyze it in plane structure, it is equations of equilibrium are 2. 3. When we analyze it in a 3D structure, when we take into consideration the structure as a 3D, then equations of equilibrium are 6. That is summation of forces in x direction, summation of forces in y direction, summation of forces in z direction. Similarly, moments about x-axis, moments about y-axis and moments about z-axis equal to 0. So, in 3D or space structure, the equilibrium equations are 6. In 2D or plane structures, equilibrium equations are only 3. So, we are talking mainly of plane structures in our structural analysis 1 as well as structural analysis 2. So, in that case, we will have only 3 equations of equilibrium. So, when we can analyze the structure, when we can find out the response of the structure using equations of equilibrium alone, that structure is known as, this structure is known as determinate structure. Determinate structure, because we can apply these equations of equilibrium and find out the analysis of the structure, find out the response of a structure. What is another example of determinate structure? Another example of determinate structure, as we have seen, is a simply supported beam. This is the simply supported beam. All of you know, one end is hinge, other end is roller. This is simply supported beam, let us say of some length L, and with some loading on it, we can analyze it. We can plot the shear force diagram, we can plot the bending moment diagram. So this is determinate structure. The first one we have seen as determinate structure, this one is a cantilever beam. This is simply supported beam. Another example of determinate structure is overhanging beam. Let us say this is a beam with one end hinged, other end roller, and it is some overhang above it. This is, let's say this length is A and let us say this length is B. So this is overhanging beam. This is also a case of determinate structure. So we have seen, what do you mean by determinate structures? Determinate structures are the structure where we can analyze the response of the structure using equations of equilibrium alone, that is summation fx equal to 0, summation fy equal to 0, summation m equal to 0. These three equations we can use and we can analyze, we can plot the shear force diagram, we can plot the bending moment diagram of these structures. What are the examples of determinate structures? Yes, you have guessed it right. Cantilever beam, simply supported beam, and this is overhanging beam are the examples of determinate structures. Now, the smart persons amongst you must have judged it very right. What is indeterminate structure? Now, let us look at what is indeterminate structure. Indeterminate structures are the structures. Naturally, if determinate structures are the structure where we can determine the structural response using equations of equilibrium alone, indeterminate structures are the structures where we cannot determine the structural response using equation of equilibrium alone. Let us consider an example of fixed beam. Let us consider an example of fixed beam loaded with something. Now, how many unknowns are there, or how many unknown things are there at our disposal? Unknown things are, there are three reactions at this end. There are three reactions at this end. So unknown things are 6. So number of unknowns equal to 6. Number of unknowns equal to 6. And how many equations of equilibrium we know? Equations of equilibrium, we know there are only 3 equations of equilibrium. There are only 3 equations of equilibrium. So this structure is indeterminate structure as number of unknowns are more than number of equilibrium. Let us say I will take an example, a simple example in mathematics, that is 2a plus 3b plus 4c is equal to 10, and if I say 3a plus 4b plus 10c equal to 100. Can you solve these equations? Let me know. Can you solve these two equations having 3 unknowns? Definitely not. Definitely not, because here number of unknowns are 3 and number of equations are 2. So we cannot solve these two equations with 3 unknowns. We want the third equation to be generated. Somehow we want the third equation. If there are 3 equations and 3 unknowns, we can solve it. If there are 2 equations with 3 unknowns, we cannot solve these equations. It's a well proven fact in mathematics, and same is the case with indeterminate structure. Yes, my friends, in last discussion we have seen indeterminate structure. Fixed beam is an example of indeterminate structure. What is another example of indeterminate structure? A continuous beam. A common example which we will come across in structural analysis, just like this. Let us say this beam is fixed at one end, hinged at the other, and then roller at this end, and this end is free, other end is free. So how many number of reactions are possible? All of us know for fixed support there are 3 reactions. For fixed support there are 3 reactions. For hinge support there are 2 reactions. Again 2 reactions. And for roller support there is 1 reaction. So number of reactions 3 plus 2 5 plus 2 7 plus 1 8. So number of unknowns to be determined, or number of unknown reactions, number of unknowns to be determined will be equal to 8. And how many number of equations are there at our disposal? Number of equations are equal to, we are not going to change it, number of equations same, 3. Summation fx equal to 0, summation fy equal to 0, summation of moment equal to 0. So in this case, this is also a case of indeterminate structure. So my friends, you must have understood the difference between determinate structures and indeterminate structure. Now my simple question to you is, which are the structures which are commonly found in our practice and why? We will discuss this issue. We will discuss this. What are the structures that are commonly found in construction and why? Why these types of structures are there in construction and why not other type of construction? I am asking about determinate structures or indeterminate structure. What is your opinion? Do you find determinate structures more or indeterminate structures more? Just think over it, and then we will discuss about whether we are getting more determinate structures in practice or more indeterminate structures in practice. Okay, we'll discuss about that issue, and we'll discuss about that explanation during our class discussion. Thank you. So my friends, in our last lecture, in our last discussion, we have seen that we come across mostly indeterminate structures in practice because indeterminate structures are economical in nature. determinate structures are not economical, indeterminate structures are economical, and the shear forces and bending moments that occur in indeterminate structures are quite less than the shear forces and bending moments that occur in determinate structures of the same span and same loading. Let us take an example. Let us take an example about this. This is the simply supported beam, okay, loaded with simply supported beam of length L, and loaded with some load, uniformly distributed load. Now let us say the bending moment is somewhere like this. Let us say this value of the bending moment, this is W kilonewton per meter. Let us say this bending moment value is P. In that case, if we fix, now simply supported beam is a determinate structure. Now this is a fixed beam of same length L. This is a fixed beam of same length L and uniformly distributed load of W per meter. In that case, the bending moment diagram will be the same, but this bending moment small p, I am denoting it small p, will be a fraction 0.1 or 0.2 of p. 0.1 or 0.2 of this p. So this is just 10% or 20% of the bending moment. We know that greater the bending moment, we require thicker sections to be planned. We have to compromise on economy of the structure. So we want lesser bending moments in the structure so that we can plan thinner sections, and in that case, that is why the determinate structures are uneconomical and indeterminate structures are economical in nature. So mainly we are learning in this semester as well as in the next semester, we are learning various methods to analyze indeterminate structure. In your previous semester, same 3, you have learned the strength of material, in which you have seen how to analyze this determinate structure. You have seen simply supported beam, we have seen cantilever beam, we have seen overhanging beam also. Now in this semester as well as in next semester, we will learn how to analyze indeterminate structure. So my friends, what are the methods of analysis of indeterminate structure? Because we get mostly indeterminate structures in nature, indeterminate structures in practice. Just because indeterminate structures are quite economical in nature, they give us lesser bending moment. This means we can plan thinner sections, and that save us economy. Okay, that save our economy. Thinner section means lesser material and our economy is saved. So methods of analysis of indeterminate structures that we are going to see. There are various methods of analysis. Each method will analyze the indeterminate structure. The first method we are going to see is 3-moment equation. It is invented by Italian mathematician Clapeyron. 3-moment equation. Italian mathematician has invented this method, 3-moment equation. So this is the method of analysis of indeterminate structure. The second method, which was developed during 18th century, was strain energy method. These are all classical methods. Strain energy method. In this semester, we are going to learn 3-moment equation, strain energy method. Now from the strain energy method, further the mathematicians and civil engineers have derived flexibility method. Flexibility method is the derivation of strain energy method, advanced level of strain energy method. Another method which is totally different from the above 3 is slope deflection method. Slope deflection method. This is the method of analysis of indeterminate structures. All these methods are the methods of analysis of indeterminate structure. Then another mathematician has invented Hardy-Cross. Professor Hardy-Cross has invented another method that is properly known as moment distribution method. Moment distribution method invented by Professor Hardy-Cross method, or some classical people, they say it's a Hardy-Cross method. Moment distribution method is another method. Slope deflection method, moment distribution method. Next, we are going to see Carney's method. Carney is another name of another scientist. He is in 20th century. So he has invented something known as Carney's method, which is a modification of moment distribution method and amalgamation of moment distribution and slope deflection method. Carney's method, then column analogy method. Next, stiffness method, and then finite element method. Stiffness and finite element. Now stiffness and finite element methods are modern methods of analysis and which are suitable for computer programming. Stiffness method, all computer programs are done using either stiffness method or finite element method, which we are going to learn in our next semester in details. in our next semester in detail stiffness method and finite element method. So friends, I have just enlisted various methods of analysis of indeterminate structure, that is the structures having more number of unknowns than 3. 3 are the number of equilibrium equations, 3 is the limit for analysis. If the number of unknowns are more than 3, we used to employ either of these methods to analyze the particular structure. We need to employ either of these methods to analyze the particular structure, out of which 3 moment equations, strain energy, flexibility, slope deflection and column analogy, these are the methods we are going to see in this particular semester, and in our next semester during our structural analysis 2, we will see Kearney's method, moment distribution method, stiffness method and finite element method.